Welcome back to the deep dive. We have a massive stack of research on the table today, and I have to say, going through this material completely changed the way I look at a simple walk in the park.
It really does.
We are analyzing How Not to Get Eaten by Josette Reeves with these incredible illustrations by Asia Orlando, but we're also pulling in a lot of, supplementary biological papers on predator-prey dynamics.
It is a heavy stack today.
Mhm.
And I think the title, How Not to Get Eaten, might trick people into thinking this is, lighthearted.
Right, a little fun.
Yeah, but when you actually dig into the mechanics Reeves is describing, it's a masterclass in military strategy, chemical warfare, material science, and physics.
That is exactly the vibe I got. We tend to Disney-fy nature, right? We see
Yeah.
the cute bunny and the green grass and think it's peaceful.
Oh, absolutely.
But the reality this research paints is that the natural world is essentially a 247 high-stakes battlefield.
It is the highest stakes imaginable.
Yeah.
There is no second place in this game.
Yeah.
You either survive to pass on your genes or you become energy for someone else.
Right. And the core concept here, the engine driving all this chaos, is the evolutionary arms race. I want to start there because it frames everything else we're going to talk about.
It's fundamental.
It isn't just that lions are fast and gazelles are fast. It's that they are locked in a feedback loop.
Precisely. In evolutionary biology, we often refer to this as the Red Queen hypothesis,
Yeah.
which is taken from Alice in Wonderland.
I love that analogy.
It fits perfectly. The Red Queen tells Alice, now here, you see, it takes all the running you can do to keep in the same place.
So you have to constantly improve just to not fall behind.
Exactly. If a predator evolves a slightly better eye, the prey must evolve slightly better camouflage just to maintain the status quo, to just break even. If they don't, they go extinct.
Wow.
And this pressure has been grinding away for millions of years, and it has produced adaptations that are, quite frankly, mind-bending.
And that is our mission for this deep dive. We aren't just looking at running away. Running is, it's boring in this context.
It's the simplest solution, but not always the best one.
We are looking at the ingenious, the disgusting, and the psychological warfare animals use to stay off the menu. We're talking about dance routines that confuse biological computers, invisibility cloaks that fool physics, and weapons made of, bodily fluids.
We definitely have some gross biology to cover today.
I do. But let's start at step one. Before you can deploy a chemical weapon or hide in a hole, you have to know the threat is actually there.
You have to.
We need to talk about assessment.
Situational awareness. It's the foundation of the pyramid. If you fail at detection, the rest of your arsenal doesn't matter.
And the sensory adaptations in the notes are wild. The woodcock caught my eye immediately. It's a bird, it looks a bit goofy, but its vision is engineered for a very specific problem that I hadn't considered before.
It solves the head-down problem. Think about how a woodcock feeds. It probes its long beak deep into the mud to find worms.
Right.
So functionally, its face is buried in the dirt. In most animals, that is a death sentence. You are blind to the world and your neck is exposed.
You are basically serving yourself up on a platter to a fox or a weasel.
You made it easy for them.
Mm.
So, the woodcock's eyes have migrated. Over evolutionary time, they have moved way up and far back on the skull.
Like unnaturally far back.
It looks strange, but what it does is give them a complete 360-degree field of view.
So it's not just a wide-angle lens. They can actually see behind their own head.
Literally. While its beak is underground, it is watching the sky for hawks and the horizon for weasels simultaneously. It essentially has no blind spot.
That is a serious hardware update. But it makes me wonder about the trade-off. If your eyes are on the sides of your head, you usually lose depth perception, right?
You do. You lose some binocular vision, which is what gives us that really precise 3D picture of the world. But for a prey animal, what's more important?
Spotting movement.
Just spotting movement. Knowing something is there is far more important than knowing exactly how far away it is. The priority is detection, not precision targeting.
Get the alarm bell, not the exact coordinates.
Exactly. You just need to know danger and direction. The rest you can figure out as you fly away.
That makes sense. Now, speaking of detection, let's talk about the caribou, or reindeer. This one seems to have a software update regarding light physics.
This is one of my favorite examples of environmental adaptation because it deals with the invisible spectrum.
The world we can't see.
Right. Think about the Arctic environment. It is white, snow everywhere. A polar wolf is white. To a human eye or a standard camera, that wolf is effectively invisible against the snow.
White on white. It's the perfect camouflage.
For us, yes. But the caribou has evolved to see into the ultraviolet spectrum. Now here's the physics kicker. Snow reflects UV light brilliantly.
Okay.
It's like a mirror for UV. But fur, even white wolf fur, absorbs UV light.
Ah, I see where this is going. So the background is glowing, but the wolf is a black hole.
In the UV spectrum, yes. To a caribou, that invisible white wolf looks like a stark, dark silhouette against a bright neon background.
It stands out more than it would if it were, say, brown.
Exactly. The camouflage completely fails. It backfires.
It's like they have built-in thermal imaging, but for UV. It completely flips the script on the predator strategy.
It does. And it's a great reminder that camouflage is relative. It only works if your enemy sees the world the way you think they do.
Yeah.
If the observer changes their visual spectrum, your camouflage might actually make you stand out more.
It's an evolutionary chess move. You think you're invisible, but I've changed the rules of the board.
And the wolf doesn't even know.
Moving from sight to sound, we have to talk about the harbor seal. This isn't just about hearing. Well, this is about data analysis under pressure.
It is acoustic discrimination. So harbor seals have a major problem. Orcas. Killer whales.
Right. Top predator in the ocean.
But not all orcas are the same. They have distinct cultures or ecotypes. You have resident orcas, which eat fish and couldn't care less about seals.
They're just neighbors.
Exactly. And you have transient orcas, also known as big killer whales, which are seal hunting specialists. They are marine mammal assassins.
So one is a murderer, the other is a harmless neighbor.
And visually, if you are a seal in the water, an orca fin looks like an orca fin. You can't tell them apart easily from a distance.
Too late by the time you can.
But vocally, they are distinct. They have different dialects. The research shows that harbor seals can distinguish the specific calls of the seal-eating pods versus the fish-eating pods.
That is a high-stakes discrimination task.
It is vital energy management.
Right.
Think about it. If you panic and haul out of the water every time a fish-eating orca swims by, you are wasting energy you need for hunting or keeping warm.
You're constantly on high alert. It's stressful.
You can't afford to cry wolf or cry orca when there is no danger.
Yeah.
So they filter the data. They hear the calls, identify the dialect. Fish eater, stay chill, seal eater, evacuate the pool immediately.
It's knowing the difference between the sound of a delivery truck and a tank.
That is a perfect analogy. And it shows that prey animals aren't just reacting blindly. They are processing information and making calculated decisions based on experience.
We can't leave the assessment phase without talking about the crickets. This blew my mind because I always assumed insects were just kind of reacting to motion. But the cricket has a dedicated early warning radar system.
The Circe. If you look at a cricket, those two little spikes on the rear end, most people think they are stingers or just weird appendages.
Yeah, I've always wondered what these were.
They are actually aerodynamic sensors.
They measure wind.
They measure air displacement. They are covered in these things called filiform hairs that are incredibly sensitive to drag. When a predator lunges, even a spider, which is very fast and relatively small, that movement pushes a tiny wave of air ahead of it,
A pressure wave.
a micropressure wave. The Circe detect that subtle change in air current and trigger a reflex circuit in the cricket's nervous system. It's hardwired.
So it's not even a thought.
The cricket jumps before its brain even processes the thought, there's a spider. It's a bypass circuit. Signal from Circe straight to leg muscles. Jump.
So it is a physical spidey sense.
It is faster than thought. If they had to think about it, oh, is that a spider? Should I jump? They would be dead. The physics of the air saves them.
Okay, there are so many more sensory examples we could cover, like the damselfish sniffing for danger or the ladybug sensing a goat's breath.
Yeah, the ladybug one is amazing. They can sense the heat and humidity change just before the goat chomps down on the grass they're on.
Incredible. But the point is made. Detection is step one. But sometimes you don't need to run if you just disappear. Let's move into the first major defense strategy in the book, the art of invisibility.
Camouflage and masquerade, the twin pillars of hiding.
The book makes a distinction here that I think is important. Camouflage is, I am the background. Masquerade is, I am a specific, boring object.
Correct. Cryptic coloration, or camouflage, is blending in. The bittern is a classic example. It's a bird with a streaky brown body that just melts into a reed bed.
But it's not just the color, right? It's the behavior.
That's the key. It points its beak straight up to the sky, so its body and neck stripes align perfectly with the vertical reeds. And if the wind blows, it sways.
It sways with the reeds.
It becomes another reed in the bed. That's the behavioral component that makes the visual camouflage work.
And then you have the tapir babies. The adults are just one solid color, gray or brown.
Solid targets. But the babies have these wild stripes and spots. It looks like a watermelon.
It does. So why the different outfits?
because the baby needs to hide while mom is off foraging. Those spots and strikes perfectly mimic the dappled sunlight on a rainforest floor. A jaguar or a puma looks down, and their brain just edits the baby tapir out. It's just light and shadow.
It's a temporary defense for their most vulnerable stage.
And a great example of evolution in action is the rock pocket mouse. Most of them are a sandy color to match the desert. But in areas with black volcanic rock,
They're black.
they evolve dark fur. It's a textbook case of natural selection. The sandy ones on the black rock get picked off by owls, the black ones survive, and over time, the whole population changes color.
So that's blending in. But then there's masquerade, which feels more like a con job. And the mastery of it in insects is startling. You have the oak leaf butterfly.
The photos of this are uncanny. It doesn't just look green or brown.
No, it's high definition. It isn't just leaf-colored. When the wings close, you see a midrib vein running down the center. You see distinct side veins.
You see splotches that look like fungal decay. Some even have transparent spots that mimic holes where worms have eaten through the leaf.
They are mimicking the imperfections of a dead leaf. That is the genius part. If it were a perfect leaf, it might look suspicious.
Exactly. It mimics a rotting, worthless piece of vegetation. A bird isn't looking for trash. It's looking for a juicy insect. And then, purely for the wow factor, if they open their wings, they are bright orange and blue.
Total contrast.
But the moment danger appears, snap, they become trash on the forest floor.
Then you have the bird-dropping spider, which, look, I respect the survival strategy, but it is gross.
Selenia excavata. It is committed to the bit. It's not just colored white. It bunches its legs up against its body to create an irregular, lumpy shape. It's wet and glossy. It is colored white and black, specifically to look like a splat of avian excrement.
Because the one thing a bird is definitely not going to eat is its own poop.
It is the ultimate safe zone. But think about the behavioral discipline required here. If a piece of poop starts walking across a leaf, the jig is up.
Walking poop is suspicious.
Exactly. Motion breaks the illusion. So this spider has to remain perfectly still during the day. It effectively shuts down. It only hunts at night when the visual masquerade isn't needed.
That is a serious trade-off. You lose half your day. You can't feed, you can't mate, you can't move. You just have to sit there and be poop.
Survival always costs something. In this case, it costs time and opportunity.
And there's also the triple-tail fish, right? The young ones.
Yeah, they use masquerade for both defense and offense. They turn on their side and float near the surface, near mangrove roots. Their yellow, mottled color makes them look exactly like a fallen, decaying mangrove leaf.
So other fish ignore them.
They ignore them, and smaller fish might even come to investigate the leaf for shelter, and then the leaf eats them.
It's a Trojan leaf.
It's a perfect ambush predator disguised as garbage.
Now, if we are talking about the kings of camouflage, we have to go underwater. The cephalopods, cuttlefish, squid, octopus. The research here pushes the boundaries of what we think is biologically possible.
They're operating on a completely different level. A chameleon is slow. A chameleon takes minutes to shift colors, and it's usually based on mood or temperature, not conscious control.
Okay.
A cuttlefish changes in milliseconds. We're talking 200 milliseconds. It is video rate refreshing.
And it is the mechanism that is fascinating. They have these pixels in their skin.
Chromatophores. Think of them as tiny elastic sacs of pigment red, yellow, brown. Each sac is attached to a tiny radial muscle controlled directly by the nervous system.
So they can individually control millions of these sacs?
They can stretch the sac open to show the color or shrink it down to a tiny dot to hide it. They are manually operating millions of pixels.
It's a biological television screen.
And underneath that, they have reflectors, iridophores, and leucophores that bounce ambient light back to create blues, greens, and whites. And on top of that, they have papillae. This is the part that always gets me. They can change the 3D texture of their skin.
Right. The book mentioned this. They can go from smooth skin to spiky skin to match a rock.
In seconds. They use hydrostatic pressure to push up these little bumps, so they swim over a piece of coral, and they don't just match the color and pattern, they match the bumpy texture of the coral.
It's a biological LCD screen that is also a 3D printer.
It's almost impossible for us to comprehend that level of control. They're wearing the environment.
But there was one detail about the cuttlefish that felt like pure sci-fi. The invisible energy defense against sharks.
This is amazing. So sharks are apex predators because they hunt using multiple senses. Vision, smell, but also electroreception. They have organs called the ampullae of Lorenzini that detect the faint electrical fields generated by muscle movement and ion exchange in living things. Every heartbeat, every gill movement creates a tiny electric pulse.
So even if the cuttlefish is visually invisible, the shark can hear its electricity.
It can feel the cuttlefish's heartbeat. It can feel its gills moving. It's a dead giveaway. So when a common cuttlefish sees a shark, it freezes visually. But it goes further.
What does it do?
It stops breathing. It slows its ventilation to near zero. And then, this is the kicker, it wraps its tentacles around its siphon and body openings.
It is sealing the leaks.
It is physically blocking the ions from escaping into the water. It effectively creates a biological Faraday cage to mask its bioelectric signature. It's holding its electrical breath.
It knows the shark can see its electricity. That implies a level of evolutionary awareness that is staggering.
It is a specific adaptation to a specific predator's supersense. It shows that the arms race happens on every spectrum: visible light, sound, and yes, electricity.
And speaking of specific adaptations, let's look at the Hawaiian bobtail squid. This one uses light to hide, which sounds counterintuitive. Usually, light makes you visible.
This is called counter-illumination, and it's all about silhouettes. If you are a small squid swimming at night and the moon is above you, you cast a shadow downwards.
You're blocking the light.
Exactly. A predator looking up from the deep sees a dark silhouette against the moonlight. You are a target.
So what's the solution?
The bobtail squid has a light organ on its belly, but it doesn't just glow randomly. It has a symbiotic relationship with a specific bacteria Vibrio fischeri that produces light.
So it farms its own light source.
It does. And the squid has photoreceptors on its back that measure the intensity of the moonlight coming from above. It then tunes the bacteria to match that brightness exactly, pointing downwards.
So it fills in its own shadow.
It erases its shadow. From below, looking up, you see moonlight, and where the squid should be, you just see more moonlight. It is a cloaking device powered by bacteria.
Just incredible. We have to touch on the harlequin filefish before we move on. It combines everything.
It's the multi-tool of camouflage. First, visually, it has polka dots and colors that perfectly match the coral polyps it lives on.
Standard camouflage.
But then it has chemical camouflage. It eats so much of this one specific type of coral that its body starts to smell like the coral.
So a predator, like a cod, which hunts by smell, swims right past it.
It smells the reef, but it doesn't smell a fish. It's an olfactory invisibility cloak.
Yeah.
And then there's the behavioral part. It sleeps attached to the coral, smoothing down its fins to look less fishy. It's visual, chemical, and behavioral deception all in one package.
That is the total package. Okay, so that is the solo game, hiding. But sometimes you can't hide. Sometimes you're out in the open. That is when you need a team. Segment 2, strength in numbers.
Group defenses. And the simplest form of this is the dilution effect. It is a cold numbers game.
It sounds callous. I don't have to be faster than the bear. I just have to be faster than you.
That is exactly what it is. The sockeye salmon smolts are a prime example. When the young salmon migrate from Choco Lake to the Pacific, they do so in these massive rivers of silverfish. Millions of them.
A huge pulse of biomass.
And the predators, bull trout, birds, bears, they're waiting. They're going to eat. They will get some salmon, but they can't eat a million.
They get swamped. Their stomachs are only so big.
It's called predator satiation. The sheer volume overwhelms the predator's capacity to consume. So the individual's chance of survival goes up purely because of the crowd size. You are 1 in a million, literally. It's safety and statistics.
But some groups are doing something more active than just being a crowd. The starling murmurations. We have all seen the videos, those shifting liquid shapes in the sky. It looks like a lava lamp made of birds.
The bedtime boogie.
Is that really the scientific term?
It is the charming term used in the book,
Mm.
but the function is deadly serious. It's an anti-lock-on mechanism. Think about a peregrine falcon or a marsh harrier. They are aerial predators that hunt by locking onto a single target and diving at incredible speed.
High-speed collision.
Right. But if the target is constantly splitting, merging, swirling, and shifting density, the predator's visual processing gets overloaded. It's the confusion effect. Where do you aim? The predator hesitates. And in the wild, hesitation means starvation.
And the math behind this is fascinating. The birds aren't telepathic. There is no leader bird shouting, "Turn left."
No, not at all. It is complex behavior emerging from very simple rules. Computer models have shown this. Each bird tracks the 6 or 7 closest neighbors. That's it.
So it's just reacting to its immediate vicinity.
If they turn left, I turn left. If they speed up, I speed up. That simple rule cascades through the flock of 10,000, 100,000 birds in milliseconds, creating those beautiful fluid waves.
It is a distributed algorithm. A decentralized intelligence.
It is. No one is in charge, but everyone is coordinated.
Now, sometimes the group defense turns aggressive. We see this with sperm whales.
Against orcas, again, sperm whales are huge, but a pod of orcas can and will hunt them. So they have a defensive formation called the Marguerite Formation.
Like the flower.
Exactly. They form a circle, like the petals of a daisy. All the adults face inwards, with their tails pointing out. In the center of that circle are the calves, the vulnerable young.
So they've created a fortress of tails.
A fortress of incredibly powerful tails. If an orca tries to attack, it's met with a wall of flukes that can deliver a bone-shattering blow. They create a safe zone in the middle and a kill zone on the outside.
And we even see this kind of active rescue with monkeys, right? The white-faced capuchins.
Yes, there are documented cases of capuchin troops physically attacking a predator, like a boa constrictor that has captured one of their members. They will bite and mob the snake until it lets go. They don't just abandon their own.
That's a huge risk for the individuals doing the mobbing.
It is, but it reinforces the social bonds and increases the overall survival of the group.
But the most extreme example of aggressive group defense has to be the Japanese honeybees. This is a horror movie for the hornet.
The bee ball. This is a classic case of an evolutionary arms race, where the prey found a loophole in the predator's armor.
Okay, set the scene. You have the giant hornet. It's a monster.
The Asian giant hornet is a tank. It is heavily armored. A single bee stinger simply cannot penetrate its exoskeleton. It's a killing machine. A scout hornet finds a beehive, marks it with pheromones, and brings the squad.
And that's it for the hive?
For most hives, yes. A small group of hornets can slaughter 30,000 European honeybees in just a few hours.
It is a massacre. The European honeybees just get wiped out, right?
European bees panic. They try to sting, they fail, they die. They have no evolutionary history with this predator. But the Japanese honeybees co-evolved with this hornet. They have a trap.
They let the scout in?
They invite the scout in. They don't attack it immediately on the landing board. They let it enter the hive. And then, on some unseen signal, hundreds of bees swarm the hornet instantly.
A bee ball?
They create a tight, dense ball of bees, completely encasing the hornet. The hornet is trapped inside.
But they aren't stinging it. That doesn't work.
Stinging is useless. Instead, they start vibrating their flight muscles. They're not flapping their wings, just shivering intensely. This generates heat. They turn the center of that ball into a convection oven.
They cook it.
They raise the temperature to exactly 115 degrees Fahrenheit or 46 degrees Celsius. At the same time, the bee ball increases the carbon dioxide level, which further weakens the hornet.
But how did the bees survive that temperature?
Now, here's the biological precision. The hornet dies at 115 degrees. The bees can survive up to about 118 or even 120 degrees Fahrenheit.
That is a razor-thin margin.
It is thermal brinkmanship. They know the exact lethal temperature of their enemy and their own tolerance. They cook the hornet to death using their own body heat, stopping just a few degrees short of cooking themselves.
That is incredibly risky, but effective.
It kills the scout before it can summon the rest of the hornets. It saves the hive. But it requires total, selfless group coordination.
Communication is key in these groups. I love the meerkat example because it shows a sophisticated language.
It isn't just danger. The meerkats have semantic alarm calls. The calls contain specific information. They have a specific sound for eagle, which means look up and run to a hole.
A different call for a ground predator.
A different sound for jackal or snake, which might mean climb a tree or mob the predator. They even have calls that indicate the distance of the threat. It is actionable intel.
So it's not just an alarm, it's an instruction.
Exactly. But my favorite part is the watchman's song. Being a sentinel is boring. You stand there on your hind legs while everyone else digs for food. But the sentinel makes a constant, soft peeping sound.
It is an all-clear signal.
It is a heartbeat. It tells the foraging group, I am on duty, I am awake, you are safe. And the research shows that the foraging meerkats spend less time looking up and more time eating when the watchman is singing.
Because they trust the system.
The moment that song stops, the group panics. That allows them to eat efficiently because they trust the audio feed from their security guard.
There are so many other examples of communication, like the crested pigeon's whistle feathers.
Yeah, that's a mechanical sound. Specialized feathers make a high-pitched whistle, but only when the bird is flapping hard, like in a panic takeoff. Yeah. So the sound of flight itself becomes an alarm call.
Genius. And then there's symbiosis, the odd couple defense, the pistol shrimp and the goby.
This is the beautiful partnership. The pistol shrimp is an amazing digger. It creates and maintains this perfect burrow, but it's nearly blind.
So it's a great architect, but has no security system.
And that's where the goby comes in. The goby fish is the lookout. It has excellent eyesight, so it sits at the entrance of the burrow. The shrimp keeps one of its long antennae on the goby's tail at all
A
times.
physical connection.
A data cable.
Yeah.
If the goby sees danger, it flicks its tail in a specific way. That signal travels down the antenna, and both of them shoot back into the burrow in a split second.
And they sleep in there together.
They do. And the shrimp often seals the entrance with a pebble for the night. The goby gets a safe house. The shrimp gets a pair of eyes. Perfect symbiosis.
Trust in the system. Okay, let's pivot. Sometimes you are alone and you aren't invisible. You just have to be tough. Segment 3. Armor and architecture.
Hard defenses, making yourself too difficult to eat.
The Arapima fish. This thing is a dinosaur.
A living fossil in the Amazon. It can grow up to 10 feet long, and it has to survive inside waters infested with piranhas.
Whose teeth are legendary.
Piranha teeth are like surgical shears. They shear through flesh. So the Arapima needs armor.
But not just plate armor, right?
No, because if you wear a simple ceramic plate and get hit with a hammer, it might crack. The Arapima scales are a composite material. The outer layer is mineralized and very hard that deflects and blunts the initial bite.
The first line of defense.
But the inner layer is made of collagen, arranged in a bulligan structure. It's like a spiral plywood. It's tough, but flexible.
So it is flexible.
It absorbs the energy of the bite. The hard outer layer stops the penetration, and the soft inner layer deforms without breaking, spreading the force out. It is exactly the same principle we use in modern ballistic vests and tank armor.
Nature engineered Kevlar millions of years ago.
Convergent engineering. Physics is the same whether you are a fish or a tank designer.
What about the West Indian fuzzy chitin? The name is adorable, but the biology is weird.
It is a mollusk. It looked like a little armored slug that lives on rocks in the intertidal zone. But its shell, which is made of 8 overlapping plates, is studded with hundreds of tiny black dots.
I saw pictures of this. What are those dots?
Those are eyes.
Eyes on the shell.
Eyes made of the shell. The lenses are made of aragonite, which is a mineral, the same mineral as the shell. They are rock eyes.
So it can see through its own armor?
It can. They aren't high definition. They probably can't read a book, but they can detect a shadow or movement from about 2 meters away.
And then what does it do? Clam up.
It clamps down onto the rock with its muscular foot so hard that nothing can pry it off. It sees you coming with its rock eyes and becomes a part of the rock.
Amazing. There's also the burrow plug gecko.
Oh, this is a great one. This gecko hides in spider burrows, but the burrow is bigger than its head. So how does it protect itself?
It plugged the hole.
With its tail. It has this thick, bony, shield-like tail covered in spiky scales. It backs into the burrow and uses its tail as a manhole cover. A predator comes along and just finds a sealed, spiky door.
Some animals don't have permanent armor, though. The water fleas, they have armor on demand.
Inducible defenses. This is so efficient. Water fleas, or Daphnia, are tiny crustaceans. They only grow defensive armor-like spines or a pointy helmet when they smell predators in the water.
They smell them.
They detect the chemical cues, the chiromones, released by predators like stickleback fish. If the coast is clear, they don't waste the energy building armor. If predators are around, they grow the spikes, which makes them much harder to swallow.
It's a smart factory for armor. Only build it when you need it.
Exactly. Don't pay the cost unless there's a threat.
Then you have the ballers, the ones that roll up, like the pangolin.
The pangolin is the ultimate defensive ball. It's covered in these large, overlapping scales made of keratin, just like our fingernails. But they're sharp and incredibly tough.
So it rolls into an impenetrable ball.
An almost perfect sphere. Even a lion can't get through it. And the tail can snap shut with incredible force, like a vice, which can injure or trap a predator's paw or snout if they try to pry it open.
And the armadillo lizard does a similar thing.
But a little differently. It's covered in spiny scales, and it bites its own tail to form a tight, spiky ring. It protects its soft underbelly and presents a mouthful of spines to any mongoose that tries to eat it.
The original Ouroboros.
And this strategy is ancient. Trilobites, which are extinct now, were the original ball rollers. The fossil record shows this strategy is 500 million years old.
Wow. Now let's talk about the architects, the ones who build their armor. The caddisfly larvae.
These are aquatic insects, and they are basically little underwater masons. They spin silk, but they use it as mortar to build protective cases around their soft bodies.
What do they build with?
Whatever is available. Some use tiny pebbles, some use grains of sand, some use twigs or snail shells. They build these intricate, durable mobile homes.
So a fish just sees a pile of rocks walking around.
Exactly.
Yeah.
But the award for most creative building material has to go to the palmetto tortoise beetle larva. I feel like we have to talk about the fecal shield. We have to. It is too strange not to.
This is a soft larva. It should be an easy snack for an ant or a jumping spider.
It should be. But it has a very special adaptation. It doesn't discard its waste. It retains its own poop.
Okay.
It extrudes feces in long, stringy coils. And it has a specialized anal fork, a structure on its rear end, that catches this waste and weaves it into a dense mat,
It weaves a shield of poop.
a mobile shield. And it holds this shield over its back like an umbrella. If an ant or a predator approaches, it tilts the shield towards the threat.
So it is a physical barrier, but surely it is also chemical.
Oh, absolutely. It's made of digested plant matter that is often toxic. And it smells terrible. It is a gross-out defense combined with a physical wall.
I will touch you with this poop if you come closer.
It's a compelling argument. It's psychological and physical warfare using a weapon made of trash.
Speaking of psychological warfare, that is our next segment. Sometimes the best defense isn't a wall, it is a lie. Or a threat.
Warning signals and mimicry. This is where evolution gets manipulative and starts playing mind games.
Let's talk about apostematism, the concept of honest warning.
In nature, being conspicuous is usually bad. Bright colors get you eaten. Unless you are dangerous,
Then you want to be seen.
then you want to be a billboard. You advertise your danger. Red, yellow, black, white. High contrast colors that shout, I am toxic, I am venomous, eating me will be the last mistake you ever make.
Like the fire salamander, bright yellow and black.
Advertises its toxic skin secretions. Or the monarch butterfly, which is bright orange. The caterpillar eats milkweed, which contains cardiac glycosides.
Heart poison.
Exactly. The caterpillar and the butterflies sequester those toxins. A blue jay that eats a monarch vomits violently and learns never to touch another orange butterfly again.
It's a learned response. The warning only works if the predator can learn.
Right, which is why some animals use sound. The porcupine has black and white quills, which are a great visual warning at night. But before it attacks, it rattles its tail quills. It's an audible warning. I'm here, I'm dangerous, back off.
And the most famous visual warnings are the poison frogs.
The golden poison frog.
Mm.
So bright yellow, it almost looks artificial. It screams, I am not food. One frog carries enough batrachotoxin to kill 10 humans.
10 humans from one tiny frog.
It interferes with sodium channels in the nerves. It stops your heart. It stops you from breathing. But here's the nuance. They get that toxin from their diet.
From the mites and ants they eat.
Right. So if you take that frog and put it in a zoo and feed it fruit flies,
It becomes harmless.
completely harmless. They are not poisonous in captivity. They sequester the weapon from the environment. They don't manufacture it themselves.
So they are armed by their food. That is fascinating. It implies that their defense is dependent on their ecosystem.
It is. Their toxicity can even vary from one patch of forest to another, depending on the local insect life.
Then you have the liars. Batesian mimicry. This is where a harmless animal hijacks the reputation of a dangerous one.
It's evolutionary plagiarism.
The hoverfly is the classic backyard example.
We have all flinched at a hoverfly. It has the yellow and black stripes of a wasp or a bee. It even buzzes like one, but it has no stinger. It is a completely harmless fly.
It is a sheep in wolf's clothing.
And the detail goes deep. Wasps have long antennae. Flies have short, stubby ones. Some hoverflies will wave their dark front legs in front of their face to simulate the silhouette of long antennae.
That is incredible acting. Look at my long antenna. I am definitely a wasp.
It works. Birds avoid them. The cost of checking is that real wasp or a fake one is too high. A sting in the mouth is potentially fatal or blinding for a bird, so they skip the meal. It's better to be safe than sorry.
There is also the scare tactic mimicry, the hawk moth caterpillar. It isn't mimicking a wasp, it is mimicking a monster.
This is startling behavior. It is a big, green, juicy caterpillar. It looks like a great meal. But if you touch it or threaten it, it retracts its head into its body and puffs up its front segments.
And on those segments,
Are two huge false eye spots. It turns into a snakehead.
it looks remarkably like a pit viper.
And it doesn't just look like one, it lunges. It sways back and forth and strikes at the bird.
A caterpillar striking like a snake.
Imagine you are a small bird looking for a worm, and suddenly the worm turns into a viper and lunges at your face. You don't stick around to count the scales, you leave.
It plays on the predator's instinctual fear. It's a bluff.
A very effective bluff. The same goes for the peacock butterfly, which flashes open its wings to reveal two huge eye spots that look like an owl's eyes, startling smaller birds. or the burrowing owl, which is a bird mimicking a snake.
It mimics a snake sound.
From inside its burrow, yes. If a badger or a weasel tries to dig into the burrow, the owl lets out a perfect imitation of a rattlesnake hiss. The predator hears that sound coming from a dark hole and decides it's not worth the risk.
So smart. Okay, we have arrived at the final segment. Segment 5. The nuclear options. When the hiding fails, the armor cracks and the bluff is called. Things get violent.
Or extremely dramatic. This is the last resort.
Let's start with the Texas horned lizard. This is the one that shoots blood from its eyes.
It's a highly specialized defense against canines, foxes, coyotes, dogs. For some reason, it doesn't work as well on birds.
So how does it work?
If a coyote picks this lizard up, the lizard constricts the muscles around its eyes, which creates a massive spike in blood pressure in its head. It closes off certain veins. It intentionally ruptures the capillaries in the corners of its eyes.
And it squirts a stream of blood.
A targeted, high-pressure stream of blood. You can shoot it up to 5 feet, and it aims for the mouth and eyes of the predator.
And the blood is nasty.
It contains chemicals derived from the ants it eats. We think it's formic acid, but it tastes absolutely foul to canines. They will drop the lizard, gag, shake their heads, and spend 10 minutes rubbing their face in the dirt trying to get the taste out of their mouths.
By which time the lizard is long gone.
Exactly. It's a chemical deterrent delivered via a high-pressure hose made of its own face.
And then the hognose snake. This is the Academy Award performance of the animal kingdom.
Thanatosis. Playing dead. But the hognose takes it to an absurdist level. It's a multi-act play.
What's Act 1?
Act 1 is the bluff. It puffs up its neck like a cobra, hisses loudly, and makes false strikes. It tries to look big and scary if you keep coming.
Act 2.
Act 2 is the death scene. It collapses, but it doesn't just go limp. It writhes in agony. It defecates. It releases a foul-smelling musk. It often regurgitates its last meal.
It's going all out.
It flips onto its back, mouth hanging open, tongue dragging in the dirt. It might even bleed a little from the mouth. It is selling, I am a rotting, diseased corpse.
Because predators want fresh meat. They don't want a sick, dead snake.
Right. But the funny part, the tell that reveals it is acting, is that the hognose insists on being upside down.
If you flip it over.
If you gently roll it onto its belly, it will immediately, dramatically flip itself back onto its back. In its tiny snake brain, the rule is dead snake equals upside down.
Stop flipping me. I am dead. Do it right.
It is hilarious to watch,
Yeah.
but obviously very effective in the wild.
Finally, let's end with the kangaroo rat. This is the action hero ending. This little rodent lives in the desert with rattlesnakes.
And rattlesnakes are fast. A strike takes less than 100 milliseconds. Blinking takes 300 milliseconds.
So the snake strikes faster than you can blink. There's no time to react.
For us, no. But the kangaroo rat is faster. It has massive auditory buoy specialized hollow bone structures near the ears that amplify the faintest sounds. You can hear the tiny rustle of a snake tensing its muscles.
And its legs.
Its hind legs are spring-loaded. It can launch vertically into the air at incredible speed. But that's not the best part.
What's the best part?
High-speed cameras have shown what happens. The snake strikes. The rat leaps. But the snake is still coming up. So the rat twists its body mid-air matrix style and uses its powerful feet to kick the snake in the head.
It drop kicks a rattlesnake.
A precise kick that deflects the snake's jaws away from the rat's body. It uses the snake's own momentum to push itself further away to safety. It is reaction time bordering on precognition, combined with incredible agility.
That is, nature is metal.
Nature is absolutely metal.
So, stepping back from the blood squirts and the ninja kicks, what is the big takeaway here for our listener? For you?
For me, it is the realization that there is no perfect organism. Every single one of these defenses, every single strategy we've talked about comes with a tax, a cost.
The trade-off.
Exactly. If you build a heavy shell like a turtle, you are slow. You can't chase down food easily.
Yeah.
If you have bright warning colors, you can't hide from a predator that happens to be immune to your poison.
You're a walking target for that one specialist.
Right. If you rely on specialized camouflage, like the oak leaf butterfly, you can't leave your specific environment. You are locked into your strategy.
It's a series of compromises.
Evolution is a series of compromises. It is about being good enough to survive until tomorrow. It isn't about being invincible. The arms race never ends, so no one ever truly wins.
Good enough to survive. I like that. It is a little less pressure than survival of the fittest, which sounds so absolute.
It is. It's about finding a niche, a strategy that works just well enough for now.
Well, that brings us to our final thought. Thinking about all these trade-offs. If you, as a human, had to evolve one of these defenses, which one would you want?
Ooh, that's a tough one. The sheer utility of the cuttlefish's active camouflage is hard to beat. Just being able to blend into any background.
The ability to disappear during an awkward conversation, priceless.
I think I would take the kangaroo rat reflexes. Great for dodging traffic or catching a falling mug.
Definitely practical. I think I'm avoiding the fecal shield.
Wise choice.
To our listener, now you know exactly how not to get eaten. Whether you need to blend in, build a wall, or just kick your problems in the face, nature has a blueprint.
Stay safe out there.
Thanks for diving in with us. Catch you next time.